Welcome back. So, now in this case, as you can see on your slide, I have taken these measurements of laser Raman spectroscopy spectra, and this I have done essentially using laser microprobe spectroscopy equipment, where we were able to take the ice which we created at low temperature, and then what we did, we heated up. So, if you look at this is 295 degrees Kelvin, which is the room temperature water. When we cool it up, then it goes to 273 degrees, it is still water. When it changes the phase, then you can see spectroscopically there is a peak formation. This peak is at 263 degrees Kelvin, which is 10 degrees below the freezing point. And so, in this case, this is called OH stretching, and there are two OH stretching. So, if you look at in oxygen and hydrogen, there are two bonds. So, one is in phase, another one is out of phase. So, this is the in phase, which essentially formulates a very sharp peak. The out of phase has a peak, but it is very I would say it is a broad peak. So, if you look at the half power bandwidth of this peak, where we look at the band the peak height, and then go to the half of that and measure the size of the peak, that is how you get the average value of vibrational mode. So, we look at the half power bandwidth, and that is where we calculate how does it change over temperature as we heat or cool the substance. If you look at the other one is also what we call is Raman shift in OH stretching. And so, OH stretching peak, if you look at both of the peak are broad, but they are very high frequency. So, they are going at 2800 wave numbers to about 3800 wave numbers, while the lattice vibrations are essentially from 0 to about 400 wave numbers. And as you know, lattice vibrations are about the structure when it is in ice formation. So, this ice formation is when you have a lattice. As it melts, then there is no ice left, there is water, and so other one and what we look at, how does that change in terms of both the low frequency, where you know how the lattice is vibrating as a unit, and also the individual atoms that we look at stretching vibration, which is at very high vibrational level. So, with that we understand both the lattice, and within lattice each molecule how they are vibrating very high level, and that gives you full picture of it. And if you look at in Raman, we did the studies on laser Raman spectra, which I did in a spectroscopy lab myself, where we looked at the different kinds of ice and we fitted our data. So, we found that as we increased the layers of ice, went from amorphous. So, the first few layers of ice were amorphous. As you move forward, then it became crystalline. So, if you look at polycrystalline ice is represented on the top level, and the lower data is about purely amorphous ice as you increase the temperature from 70 degrees 20 degrees Kelvin to almost 120 degrees Kelvin. So, but if you look at in our case, because we are looking at the interface layer starts from amorphous and become polycrystalline. So, that is our first investigation, that interface layer behaves completely different than the bulk. If you had taken the bulk amorphous and bulk polycrystalline, it will have a different half power bandwidth shift with the temperature, and these are all the data looked at from the laser Raman spectroscopic point of view. We are looking at the shift of the OH stretching peak in the vibrationals in the low frequency vibration, lattice vibration, and see how it is going from amorphous to polycrystalline. Now, if you go forward, then we said okay, we now understand experimentally how it all is happening. So, why is it going from amorphous to polycrystalline? What is causing interface layer to behave differently than the bulk? So, we said okay, we now need to resort to molecular dynamics, because laser Raman spectroscopy can go to only micron level. It does not tell you about atomic level, because it is molecular spectroscopy, and we need information about atomic, what is happening at the atomic level. So, then we created, again using velocity autocorrelation for the simulation system, we calculated theoretical vibrational spectra. So, first thing that we did is that we calculated the experimental and vibrational spectra. One is computationally created on the left hand side, and the right hand side is all the experimental data which I conducted. So, both theoretical computational work and the experimental work was done, and then when we compare the two, what we see is that there is a very good match in terms of the peak nu 1 and nu 2. Nu 1 is in phase OH vibration, nu 2 is the nu 3 is the out of phase. So, these two peaks are very important and very well documented in experiment. So, if you look at carefully on the right hand side, which is the Raman shift, the experimental data, you can see this sharp peak is the in phase, and again we are looking here at OH stretching. So, we are looking at the molecular level, but looking at each atomic vibration. So, here you are seeing that this is OH1, this is OH2, this is nu 1 and this is nu 3, and we are looking as we go from 30 degrees to 50 degrees, 70 degrees Kelvin. So, we are very low temperatures. This is cubic ice that we are looking at, and in this case we are looking at the cubic ice again with the laser with molecular dynamic simulations. So, you can see that how these layers are showing up. So, there is a fairly good match in terms of the patterns that we are watching. We are not looking at number to number comparison here, because we are looking at the system atomic level is much smaller than the bulk that we are looking, where there are millions of atoms here. So, there is the effect of scale up, but here in this case we are looking at atomic level. So, now we look at our molecular dynamics visualization on ice and copper. Let me first go here. This is the atomic camera. So, this is where it becomes very interesting. So, these red atoms are shown the oxygens positions on these golden color atoms which are representing copper. So, initially we put them aligned and they are not in registry. What I mean by registry is that if you look at as you go forward here, then the distance between copper and copper atom and oxygen atom is not matching. So, there is a mismatch. Number one, now we understand why factor is that there is a mismatch at the interface of the oxygen atoms. So, when we relax it, so this is initial position and then we do 50,000 time step, long time step, we look at the relaxation, then we see that movement of these oxygen atoms on top of these copper atoms. So, now we are looking at what happens to the entire the water molecule. So, in this case the two white atoms, the smaller ones are hydrogen and these ones are the oxygen, the red ones are the oxygen atoms, the bigger one. So, now you can see this is the initial position and this is the position after many and we had done so many different runs on it using XMP supercomputer which we are running on the Cray XMP machine in the San Diego Supercomputing Center. Sitting at MIT, we did a lot of data crunching in supercomputers. These are all the supercomputed parameters. So, once you look at the supercomputed parameters, what you see here is that there is a shift in all these atoms, and now we want to look at what is happening. So, we look at two different ways. One is we are looking at the front view, if you say, and then this is the top view. So, now we want to look at what happened to the material as it moved around and what is the situation and why this kind of, and this is where we want to understand the adhesion. Why is this kind of behavior happening? So, now if you look at in this investigation, what we found is that ice molecules progressively get disordered closer to the copper interface from Raman spectroscopy observation. If you look at the vibrational spectra from the MD, what we find is that this is the reason, because the oxygen atoms are trying to sit on top of the copper atoms, but they cannot because of energy consideration, they move inside, but the hydrogen atoms then get all messed up with their bonds. So, there is almost, if you can see here in this picture, all these hydrogen bonds are gone into interstitial places and they have become amorphous because there is no structure to it, they are moved all around, and oxygen is also disordered. So, the first few layers are disordered, but as you move layers on top, they are ice on top of ice. So, they become polycrystalline, but because of amorphous layer at the bottom, there are more defects, there are more holes in this polycrystalline, and that is where the first layer is very tough as you try to chip off. the ice from the copper layer, because it is amorphous, it sticks very well, because it is formed no slip planes, it cannot get off, but as you move forward then it becomes. So, if you look then it becomes polycrystalline. So, MD visualization reveals that the disorder is caused by absorption of oxygen atoms at the lattice sites, causing disruption in the hydrogen bond, leading to the proton disorder. So, what we found in our calculations, that oxygen atoms has affinity to go towards the copper atoms, although it is not finding those parameters. So, it is moving, and that is causing disorder in the hydrogen material. So, what based on that, what we did, we came up with 7 or 8 recommendations for the people who were designing de-icing coating and de-icing materials. And as you know, if you go to an aircraft in the winter time, they will first put de-icing on the entire aircraft, because again on the aluminum material of the alloy of aircraft wings, if there is a formation of the ice which sticks, then the aircraft also have disastrous climb, and a lot of accidents happened earlier, and that is why de-icing has become important, and they will not fly any plane without de-icing in a winter time. So, in this case what we found is that for the people who want to design these coatings, we gave them lot of recommendations, saying that you need to make sure that the oxygen atoms do not go on top of the carbon atoms and formulate very good bond, and for that your de-icing copolymer coatings have to displace oxygen atoms in a carbon hydrogen chain. So, all of those recommendations are then used by the industry in creating new materials for de-icing. So, let me stop here. This kind of concludes the first case study, that by understanding at atomic level, we are now able to design new materials to solve the problem of icing on cables and structures. Thank you.